Hello, my name is Diana Nicoleta Grigore, and today I will be presenting weight copy and low rank adaptation for fuchsia distillation of vision transformers. This is joint work with Mariana Iuliana Georgescu, John Alvarez Justo, Torio Hansen, Andrea Iuliana Ionescu, Radu Ionescu, and the collaboration between the University of Bucharest, the Norwegian University of Science and Technology, and University of Medicine and Pharmacy Carol Davila. Let me start with the problem we are addressing. Vision transformers have shown remarkable performance, but they come at significant computational costs. The challenge we face is how to make these models smaller and more efficient while maintaining their performance. This is particularly important because in real-world applications, we often have limited computational resources and very little training data available. Current methods for model compression show poor performance, particularly in few shot scenarios. This creates a significant barrier for deploying these models in resource-constrained environments like edge devices. We propose Vicolora, which addresses these challenges through a three-step process. First, we create a smaller student model by reducing the number of layers. If our teacher has L layers, our student will have L divided by R layers, where R is what we call the intermittence factor. Second, instead of randomly initializing the weights, we carefully copy them from selected teacher layers. Next, we introduced enhanced low-rank adaptation, or LoRa, which allows us to efficiently train the model using minimal unlabeled data through the process of knowledge distillation. A key component of our setup is weight copying. We initialize the student by keeping every art layer where art is the intermittence factor previously introduced. This allows for a direct transfer of knowledge from the teacher. Rather than starting from scratch, we preserve learned features and maintain layer functionality. This gives us a strong starting point with compatible layer structure. Second, enhanced LoRa. Unlike standard LoRa, we apply it comprehensively to all transformer components, the queries, keys, values, output projections, and feed-forward networks. This comprehensive adaptation is crucial for better knowledge recovery and improved feature preservation. First, we extract embeddings from both the teacher and the student models. The teacher's weights are frozen because they act as our knowledge source. The student model has our enhanced LoRa blocks integrated after the weight copying step. During training, we compute a simple but effective loss, the absolute difference between the teacher and student embeddings. This forces the student to mimic the teacher's feature representations, but in a much more compact form. What's unique here is that we only update the LoRa parameters, the low-rank matrices that adapt each transformer component. This focused training is what allows us to be so efficient with both data and computation. After training, we integrate the LoRa parameters into the main model weights, ensuring we maintain fast inference times in deployment. This gives us both efficient training and efficient inference. We use ImageNet as our self-supervised knowledge distillation dataset, and for downstream evaluation, we perform linear probing on datasets from four domains: general, medical, natural, and aerial. As our first study, we present the importance of each component we introduced. On the first row, we compare with training a student from scratch using knowledge distillation, and we conclude it does not support the few-shot scenario. Next, we start with weight copying but do not add the LoRa blocks. This approach, weight copying and knowledge distillation, is a very strong baseline. The third ablation in each group represents the basic version of LoRa. As we can see, the improvement is minimal or there is a decrease in performance, probably as the number of parameters is insufficient to properly learn the skipped layers of the teacher. This justifies the need for our enhanced low-rank adaptation blocks. For our baseline comparison, we look at accuracy rates obtained by four state-of-the-art methods: DET, MiniVit, DMAE, and DORA, in comparison with weight copy plus knowledge distillation and Vicolora. The results are obtained using a compression factor of 2 while alternating between a self-supervised VIT-based teacher and a supervised one. The parameter alpha on the left represents the percentage of the original ImageNet 1K training set used during knowledge distillation. The base accuracy on each downstream dataset and each value of alpha is highlighted in bold. All results are based on linear probing. No state-of-the-art method outperforms the ablated version of Vicolora, which is weight copy plus knowledge distillation, suggesting that they are not able to handle few-shot scenarios. Our method surpassed them by significant margin. We employ two teachers, a supervised fit base, and a self-supervised one, and we consider two compression factors, R equal 2 and R equal 3. Results are reported with both 1 and 10% of the dataset, and as we can see, our method is able to surpass the strongest baseline in most cases. When looking on the downstream datasets, we can observe that our methods show much higher performance with very small percentages of the dataset, and the gap closes as we use more and more of the training set. When ablating the LoRa matrix rank, we observe that K is actually a hyperparameter that can control the bias variance trade-off in LoRa. Here, on the left, we look at the latent spaces of our strongest baseline and LoRa. For our method, as depicted in the figure, we can discern the spatial distributions of the out-of-domain aerial image dataset. The clusters are clearly delineated even though only the teacher features were used. The baseline, relying solely on optimization, generates dispersed clusters. On the right, we demonstrate attention rollout, which is a process that highlights the flow of attention throughout the model. In this visualization, we combine the attention heads by selecting the maximum response and discarding pixels with lower values. We examine three randomly selected classes from each ImageNet, namely Daisy, Persian Cat, and Goldfish, from the perspective of student models generated using weight copy and knowledge distillation and weight copy and low rank adaptation. The superiority of the latter becomes evident as it tends to focus more on discriminative aspects of the animals and flowers, such as petals, fur, or scales. This serves as evidence that the learned features are indeed valuable. As our approach randomly selects a percentage of the dataset to perform distillation, there is a near possibility that the training sample selected will be very similar. This would generate a situation of collapse, where all the representations will correspond to a single point in the feature space. To mitigate this, we propose adding the orthogonal strategy of k-means plus initialization, namely clustering the samples based on a distance metric and taking the cluster centers as our training base. In order to show a relevant situation for this problem, we take a very small percentage of ImageNet as a distillation dataset, namely alpha equal to 0.25. This would correspond to 3 samples per class and, as you can see in the results, although they are very low, we still surpass our ablated version, the strongest baseline. The difference in the results is minimal when applying the orthogonal strategy, so we could hypothesize that the small updates to the LoRa matrices don't actually suffer from this problem due to the strong frozen feature base they get incorporated into. On another line of work, we are interested in finding out if the student learning similar feature to the skipped layers of the teacher. To validate this hypothesis, we compute the mean cosine similarities between the skipped layers and the corresponding student ones between and after applying enhanced LoRa. The results can be consulted in the table, and it suggests that the features are indeed similar to the ones in the skipped layers, as the similarities increase after distillation. When using 512 samples for inference, we can see that a student obtained with an intermittence factor of 2 is twice as fast as the teacher, with half of its inference time. In training, although the number of parameters decreases because of the added matrix multiplications, the number of G-flops slightly increases. We proposed a novel method that can be used to obtain lighter vision transformers using a few unlabeled images. It combines weight copying and low rank adaptation in an efficient and effective manner. We conducted experiments in multiple low data scenarios using supervised and unsupervised teachers, considering multiple model compression factors. We outperformed competitors, DET, MiniVid, DMAE, and the bladed version of our approach with copy basic LoRa, and we present feature visualization samples that show that we produce more robust embeddings. Thank you.